it was really not until 1985 when the Scottish Dr. James Hutton wrote an influential book that basically introduced gradualism, or rather uniformitarianism. So that's written right here. It's a little bit of a mouthful. So uniformitarianism was a concept which states that the present is the key to the past, or that present geological processes may be studied to learn the history of how past geological processes went about. And in the book itself, he argued that the Earth would have to be much older than 6,000 years for these processes to have taken place and shaped the Earth as it is. So this would be based on the rate that they do happen in the present. Those processes take way too long in the present to do a small amount of work. So if that was to be true about all things shaped on Earth, then Earth must have been a lot older. In 1830, Charles Lyell wrote another book on geology, and this one made the role of gradual processes such as erosion, deposition, and mountain building a much more popular view. So he intensified what James Hutton had already started. Gradualism then actually became the popular view and lasted until the 20th century, which was until the discovery of plate tectonics. So hopefully you remember from chapter 2 that plate tectonics became a theory in the 1960s. So it wasn't until then that gradualism, took force and stayed as a main view. So this, again, plate tectonics explains the present motion and the present position and the origin of the continents. And again, this is based on a relatively slow process of both seafloor spreading, rifting, and also of subduction. Also, along with this, some scientists actually realized that occasionally there was evidence for the role of some catastrophic events, craters being one of the evidences that pointed out that, there must have been impacts going on. And so that is one of those things that scientists pointed out. By the time, there was also really an understanding and an agreement that during the Earth's history, there had been massive and relatively rapid extinctions of many, if not most of the species on our planet. So that must also have been, a cause for rapid catastrophic changes. 5 of these extinctions are in the relatively distant geologic past, and it is believed that another extinction is actually currently underway due to human activity, but that it started a few thousand years ago from the last deglaciation, basically, as we'll talk about it later. And this different extinctions can be seen within the image above. So every E means extinction. And we have gone through them in the first slide of this chapter. That image had a very good representation of when they happen in terms of geologic time. So, as I had said also in the first slide, you might have heard of one of these mass extinctions. Not the most massive one, but the one that happened 65 million years ago, and which caused the disappearance of dinosaurs. So, that extinction is believed to have been caused, or at least have been aided, actually by an asteroid impact of about 10 kilometers in size. So that asteroid, that body, extraterrestrial object, is believed to have been 10 kilometers in size, and it impacted somewhere in the Yucatan Peninsula in Mexico. And we'll look at it in more detail later. So that was one of the events that probably caused major changes within the planet, and it was in fact a catastrophic event, not just to life, but also to atmospheric processes, and perhaps even to some geologic processes such as eruptions and things like that. So after this idea was planted by some of the scientists, again, that you can have catastrophic events still happening within a gradual sort of idea for other processes like erosion and weathering and mountain building. So after this occurred, and the Beringer crater also being studied as a new concept came, the name of punctuated uniformitarianism rose within the scientific community. So they believed that calling it punctuated uniformitarianism was a good way to say, okay, most of the time there is a slow process ongoing, or there are many slow processes ongoing, but every now and then there can be catastrophic events that shape the Earth much, or it can change the Earth a lot in a very short period of time. Okay, so now not the whole remaining part of lecture, but a fair amount of it is going to be on mass extinctions themselves. So a mass extinction is characterized by basically a sudden loss of a large number of species, specifically plants and animals, relative to the number of species that are being added. Mass extinctions typically coincide with the boundaries of the geologic time periods in timescale, and this is because originally the geologic timescale was done using the fossil record. And once we found how to use radioactive decay to date things, then there were absolute ages that were added to the already made divisions from the previously made geologic timescale with the fossil record. So you will see that the geologic timescale doesn't have very nice even numbers. So for example, the Cambrian period started 542 million years ago, not 500 or 550, but rather 542, because it marks a point where the fossil record said that a lot of life kind of exploded. And so, or exploded in the good sense, like it emerged. So again, that is why most of the mass extinctions that we have also coincide with boundaries for those geologic periods or even eras in certain cases. So most hypotheses of mass extinction typically involve a relatively rapid climate change, which could have been triggered by plate tectonics, by volcanic activity, or by extraterrestrial impact. Or it could have been triggered by a combination of those three things. So again, those were plate tectonics, volcanic eruptions or volcanic activity, and or extraterrestrial impact and airbursts. Plate tectonics itself can influence the climate to change by shifting land masses around the globe. So as these land masses move, ocean circulation patterns change, and these will have a huge effect on climate. So with this continental movement, atmospheric air circulation will also change. However, this plays a relatively minor role compared to the ocean circulation pattern, which is the bigger one, distributing heat, or I should say, any type of heat across the world. How large volcanic eruptions have an effect as well, they can usually cause climate change in the following way. So when there are large basaltic eruptions, these will produce massive volumes of flood basalts, and I think we looked at this when we looked at volcanic eruptions in chapter 5. So these massive volumes of flood basalts, you might again remember from chapter 5 the large basalt igneous provinces like the Columbia River basalt or the Siberian traps or the Indian traps. All of those are those massive igneous provinces caused by flood basalts. And in these cases, when these eruptions occur, there is a release of large amounts of greenhouse gases such as carbon dioxide and as water vapor. And these will both overall warm the atmosphere of our world. As we looked at in chapter 12, that is what climate change does, or that is what the greenhouse gases released onto the atmosphere will do. They will keep that heat inside of the earth and typically rise temperatures. On the other hand, however, there are large volcanic eruptions of more siliceous material. Think of the explosive eruptions rather than the effusive eruptions. So remember, flood basalts happen like the eruptions in Hawaii, where lava is flowing kind of nicely and slowly across the surface, where explosive eruptions are more like the one like Mount St. Helens, where you have a big ash plume rising up above the volcano and typically exploding or erupting ash and a lot of other gases into the atmosphere. So in this type of eruptions, and more silicious type of eruptions, more explosive ones, there is a release of large amounts of sulfur dioxide and also, more importantly, a tremendous amount of ash. So this ash will typically cause reflectance of solar radiation, which is in the form of shortwave radiation, right? So as it causes the reflectance of the solar radiation, that heat that comes from the sun as shortwave radiation won't be able to penetrate and get all the way to the surface, but it will bounce back into space basically by that ash layer that is not allowing it to penetrate. So overall, when you have massive volcanic eruptions of explosive type material, you will have overall cooling of our atmosphere. So volcanic eruptions, depending on the type, can increase the temperatures or they can decrease them. So they have a two-way effect on our climate. And then finally, climate change is one of several effects of extraterrestrial impacts or airbursts that could contribute to extinctions. And we'll look at how they contribute to extinctions through impacts and airbursts as we look at the case studies of a couple of mass extinctions. Okay, so as I had said in the first slide of the video, life has existed on our planet since about 3.5 billion years ago, starting with cyanobacteria mats called stromatolites. However, it was not until the current eon, the Phanerozoic eon, that life truly flourished. The start of that eon happened about 542 million years ago, and we call it the Cambrian explosion, an explosion of life. Since that time, about 6 major extinctions have occurred, but most times 5 are referred to, the big 5 mass extinctions. The first extinction occurred at the end of the Ordovician period, as it's delineated here by the image, and that happened about 446 million years ago. This resulted in about 100 families of animals becoming extinct. And it appears as though it happened as a consequence from a major glaciation that happened in the southern hemisphere. So the glaciation obviously brings along a lot of cool climate. So this cooling seemed to have been followed by a subsequent warming that happened until the end of the Devonian period, which you're seeing right here. So this is where you have the end of the Ordovician with the glaciation, and then you have subsequent warming in the Silurian and the Devonian, and then you have the second mass extinction, probably due to the relatively fast subsequent warming. So in truth, this first extinction was kind of two in a way. So the late Ordovician and the late Devonian saw 2 big declines in the number of genera that there were.